Okay, guys, thanks for your patience today in class. That was super frustrating. I had major technical issues on my side, but I figured them out. It took a little bit, but I figured them out. So here's today's lesson, and I apologize that it's not didn't take place in class with everybody else, at least not with sound. So classifying chemical equations and writing net ionic equations. Classifying chemical reactions, sorry. So you got a couple different types of chemical reactions that we're going to discuss, and these are by no means the only types, but we have combustion, synthesis, decomposition, displacement, and double displacement. You may sometimes hear displacement and double displacement referred to as replacement and double replacement, but I'm probably going to typically use the term displacement. So here's your combustion reaction. We actually demonstrated a little combustion reaction today. It was the screaming gummy bear. I'll show you a video of that. I don't know if ours is any good. I haven't looked yet. If it's not, I'll send one of somebody else's. But combustion reactions require a carbon-based compound and oxygen. They produce carbon dioxide and water vapor. And when not enough oxygen is available, the reaction is incomplete, producing carbon dioxide and soot, as well as carbon dioxide and water vapor. This was pointed out to me that I should have just had as well as water vapor, which is correct. I just forgot to change it before I recorded this. I had something repeating itself. Another kind of reaction would be a decomposition reaction, which is when a compound breaks down into two or more simpler substances. So your binary compounds are typically going to decompose into the two elements, and your compounds made of three or more elements often decompose into polyatomic ions, etc., that sort of thing. This picture here is actually hydrogen peroxide decomposing, and you can make it decompose faster using catalyst, which we'll talk about later, which is probably what's going on in this picture, because if you put hydrogen peroxide, well, if you put the hydrogen peroxide that you can purchase in the store, which is very dilute, not very concentrated, it's not going to do this. But if you got hydrogen peroxide that was pretty pure, it would do this. So also you have your synthesis reaction, which is a singular compound forming from two or more reactants. Your reactants are often two elements or two simple compounds. This is another reaction we demonstrated in class today, and I'll see if I can get some better pictures of this. But this is a displacement reaction, a single displacement reaction. And in this particular example, it is a copper wire that is being exposed to a solution of silver nitrate. So you have a single element reacting with a compound and displacing another element from that compound. Your products are a different element and a different compound from the reactants. Your metals displace metals and your nonmetals displace nonmetals. And then we have our double displacement reaction, where you've got two compounds in aqueous solution exchanging ions and forming new compounds. One of the products must be a solid precipitate, a gas, or a molecular compound. And I believe this one here was, I cannot remember if this was aluminum or zinc, but it's in a solution of, I believe, copper sulfate, and that's copper forming as a, well, more like a, less like a precipitate when you think about a precipitate as being mixed in the solution, but definitely as a solid. So yes, a precipitate. And here is a little handy dandy memory device for your reactivity series. Your reactivity series would describe your most reactive and least reactive elements. So your potassium, sodium, calcium, magnesium, and so on would be, please stop calling me a careless zebra. Instead, try learning how copper saves gold, which these days, you know, you've got your smartphone in your pocket. That makes it a lot easier. That can always help you if you get stuck remembering. And now we talk briefly about writing net ionic equations. So the idea here is to write your net ionic equation. And in order to do so, you have to identify spectator ions and you have to check your atoms and your charges. So how do you identify your spectator ions? Well, Your spectator ion is the ion that doesn't take part in the chemical reaction and is found in solution both before and after the reaction. I'm going to show you some in a minute as part of your homework. We'll go over that. So here is Professor Dave, and I will play him for you. If he will go, there he goes. Or are we going to get another ad? We kept getting ads for jewelry today. I don't know why. Oh, come on. Oh, Professor Dave, he stood me up. Come on, Professor Dave. Well, maybe he doesn't want to play along. That's okay. I will just...
Hey, it's Professor Dave. Let's talk about solutions.
He knows a lot about the science stuff. Professor Dave explains.
A homogeneous mixture that's in one phase is called a solution. Think of something like table salt in water. If we are talking about a liquid solution, the thing that gets dissolved is called the solute. In this case, that's the salt. And the thing doing the dissolving is called the solvent. Here, that's the water. Solutions tend to retain the properties of the solvent, since solvent particles are typically much more abundant than the solute. We can say that a solute is either soluble or insoluble in a particular solvent, depending on whether it will dissolve in that solvent. Something will dissolve if in doing so, it will make favorable intermolecular contacts with solvent particles. In the case of salt, it will dissolve and dissociate so that the sodium ions and chloride ions can make ion-dipole interactions with water molecules. A nonpolar covalent compound will not dissolve in water because without a dipole, it can't make any dipole-dipole interactions with polar water molecules. That's where we get the saying, like dissolves like. Salt water is a strong electrolyte because the formally charged ions in solution can conduct electricity. Weak electrolytes only partially ionize in solution, so they conduct electricity weakly. We can use molecular equations to describe substances that transform in solution, and it will be useful to use subscripts after each compound to show its phase. There's solid, liquid, and gas, and we use the word aqueous to describe ions that dissociate in solution. This is important because sometimes ions come together to form a new compound which may be insoluble in that solvent. In such a case, we will denote that it is in the solid phase, as it will crash out of solution as a precipitate. We can write molecular equations to describe solution chemistry, but we can also use net ionic equations. This summarizes the key transformation by eliminating spectator ions, the ones that just sit in solution and don't do chemistry. To do this, we start by writing the complete ionic equation. This involves splitting the ionic compounds into their respective ions. Just remember the common charges of the ions to include the correct formal charges. Subscripts in the molecular equation become coefficients in the complete ionic equation since all the components are dissociating. Anything that's present on both sides, we can cancel out, like an algebra problem. These are the substances that don't do any chemistry. What's left are the two ions that come together to form a solid precipitate, which is a chemical change. This is the net ionic equation. In addition, sometimes we categorize these kinds of reactions as being either synthesis, where two things become one, decomposition, where one thing becomes two, single displacement, where one component swaps out, or double displacement, where two components switch places. This is just good vocabulary to know. Let's check comprehension.
Good old Professor Dave. So last thing we're doing is checking ions and charges, and then we move on. So here, let's get over here. I don't know if I corrected, I think I did. We found a couple little typos in here today. So your spectator ions are the ions present in solution in which a reaction is taking place, but they do not participate in the reaction. And I'm going to go ahead and put your answers up here for you to check. You can pause the video to check them. And then moving on to part A of number 3, your spectator ions. And I'll just do A through F and let you guys have a minute to look over. And you can pause the video if you need to. And that's that. I'll try to see if I can add some other stuff for you guys as far as what we did in class today with our demos outside. All right, you're all done. Thanks, bye. Okay, we're going to try this again because we had major microphone issues in class today. And it took a little sleuthing to figure out what the problem was, but we've got it fixed. So, controlling chemical reactions. So how do reactions get started? This is actually a question someone asked on their homework. Typically, your activation energy right here that we're talking about, all reactions require activation energy to get started. Most of the time that comes in the form of thermal energy, but not all the time. So the minimum amount of energy needed to start a chemical reaction is your activation energy. And all chemical reactions require a certain amount of activation energy to get started. So when we start looking at those graphs, for example, that were part of your homework, you'll see that it's a little hill shape, and that's because you have to reach a certain amount of energy before you can start the reaction. So what affects the rate of chemical reaction? Well, there's a couple of different things. There are factors such as surface area, temperature, concentration, the presence of catalysts and inhibitors. So let's look into surface area. So the reason I chose this picture, and we talked about this in class, is that there are some leaves here, and they're a great example of how a chemical reaction can proceed at a faster rate when you have greater surface area. Trees really take advantage of this. So the chemical reaction that goes on inside of leaves that we're discussing at this point would be photosynthesis. And these are leaves of a deciduous tree. So that's a tree that sheds its leaves in the fall. So having these nice big flat leaves is really helpful because it can allow for faster reaction rates and within the time frame that the leaves are actually on the tree, which is limited, you can get more reaction done, which means you can produce and store more energy. If you think about a lot of evergreen trees, like pine trees, for example, they have a decreased surface area in their needles. Their leaves are needles, and they keep their leaves all year round. So they have 365 days in which to get the same amount of energy produced and stored as trees with leaves have in the spring and summer months. Another thing that can affect the rate of reaction is temperature. Increase in temperature typically increases the speed of reaction, and this is because when you increase temperature, you increase the kinetic energy of the molecules or particles, whatever they may be, atoms within the substance, and when those start moving around faster and faster, they're more likely to bang into each other, and that will increase the speed of your reaction. Likewise, and conversely, I guess, decreased temperature is going to decrease the speed of reaction because everything is moving slower. Another thing that affects the rate of reaction is concentration. So concentration is how much of something or the amount of a substance in a given volume. And increased concentration is going to increase the speed of reaction. And if you think about there being a certain amount of particles present within a solution, for example, so like look at one of these flasks and think, okay, well, there's a certain amount of particles of my reactants available in that solution right there. So if I have more of them, they are more likely to come in contact with each other versus if I have less of them or a decreased concentration, we are going to end up decreasing the speed of our reaction because it's less likely that they're going to bump into each other. When we decrease concentration on purpose, it's typically called diluting, and we can do that with water. In the lab today, we used some diluted hydrochloric acid, and that had been diluted with water. Catalysts and inhibitors. So catalysts are going to increase the rate of your reaction. Inhibitors are going to decrease the rate of your reaction. Sometimes you want your reaction sped up, and sometimes you want it slowed down. And then also you have biological catalysts called enzymes, and they function to increase the rate of reaction inside your body for all the various chemical reactions that your body completes on a regular basis. So if we look at our homework real quick, I will show you, whoops, sorry. I'm going to make sure that you guys got the answers for this. And, sorry, I have too many things up. Okay, here we go. So for your homework, you guys had two graphs. One was an endothermic reaction, one was an exothermic reaction. So here's how these function. When asked the question, use what you know about endothermic and exothermic reactions to explain the differences in the graphs above. So what you're going to notice is that both of these reactions are going to require activation energy to get started. Your activation energy is added like right about here, and it starts to increase until it gets to this tipping point. Same thing here. And what you will notice is that in the exothermic reaction, your reactants have higher energy than your products. And in your endothermic reaction, your reactants have lower energy than your products. So the reason why your activation energy is pictured as a hill is because, as we were saying, you need to build up to the point where your reaction can take place. And then explain how adding heat to reactions shown in the diagrams would change the rate of chemical reaction, and name two other ways you could change the rate. Well, typically if you're going to add heat, well, usually your thermal energy is what's going to start your activation energy, though, like I said, not always. But if you add heat, it's going to speed up your reaction. And some other things you could do is you could add a catalyst to speed it up or an inhibitor to slow it down. You could also increase the surface area. So here, I'll leave this up for just a second so you can check these, but these are book answers basically. Okay, I think that covers all of that for you guys. Sorry about the microphone issues today. That was a nightmare, but we got it. Thanks. Two, three. Now blow gently.
Yummy.
Jack, move your hand so we can see what you've got. So there you go.
Jack, it's
There, they're going. Keep going. You might have to take a couple breaths and do it a couple times.
Guess what? I have told you. What kind of easy making?
Careful. You're fine.
Jack, it's okay for you to drink.
No, it's not.
Drink it.
So check out what's going on with Alex, though. What's he? Look at that. If you keep blowing, it should go all the way
I
down.
got it all on my paper.
Oh my gosh.
I'm too focused on Alex.
There we go. So who had the water with I?
I think it was Alex.
Smart Alec. Yeah, very clearly. Alex has.
Alex over there.
Let's see.
I'm still trying it. Keep
Well,
doing it.
yellow. Very good. See it? It's already. See how it's already dark now? It's no longer copper. Keep watching. It's gonna grow. It'll be really cool. It'll get really fat, actually.
You'll get there.
It's one of those little broccoli you eat in water.
Whoop! He shot out! That never happened!
Where'd he go?
It's like a cannonball. Get in there.
Oh.
Get in there.
How did you
That was crazy! They don't ever do that. Oh, he's sliding. Uh-oh. He's sliding to his death. Come on.
Hey, we don't encourage suicide here.
Yes, we do.
Drew.
Wait,
Drew.
He's sliding to his death slowly. That's funny. I've never seen one do that. They usually just.
Oh, there we go.
Woo!
Whoa.
Whoa, what the heck?
But he was definitely screaming. Okay, wait.
Half of it got out.
Let's try the lemon guy.
Wait, okay.
The red one wanted to live too much.
Pull more
You gotta put a
chemicals.
different one in.
No, it's still good. It's still got
Love
that.
the exit.
That was weird.
I should have. He already died.
Hey, Michael, you want to eat the charred ones? Go for it.
Actually, can I? That's a good idea, Michael.
If you bet me money, I will 100% eat the charger.
How much money?
I am.
Get in there. Go,
I will give you
go, go.
Drew, yelling go is not going to do it. Mom, try opening one of the tongs, like try opening the tongs and then sticking one end of it down.
No, I'm not doing that. That'll get him. He won't come out of there.
Come on, scream.
Look at him. He won't scream.
You might need another resume
There he goes.
It's slow. You're acting like a robot.
This is not.
Just put your mask on. Big return.
Hey, if there's ever a fire, you get on the floor, okay? So heat rises.
You're also like getting every bit of the smoke ever.
That's crazy.
I know how that works.
That smells good.
Well, it's all kicked in there, and it won't
Your
come
video
out.
got
so
pretty bad, Mom.
Let's go. Oop! He jumped again. Is he gonna slide back down?
Yeah.
He's coming.
He's
sliding.
He slides down. He's down. It's a trampoline. Yeah. Flying.
There you go.
Why are you standing in front of it?
That
Yay!
smells so good.
I think I was supposed to break the ring.
Yeah, I couldn't get him on right. Don't worry about it.
So sodium carbonate hydrochloric acid. Do we put carbonate? Okay, so what happened? There we are.
A little bit more. Now stir it. I close it up. And am I done stirring yet?
I think you're right. Or
It's like water.
Wait, but we could put this in and see if it burns it. It's a phone call, especially not in.
No, I accidentally put it down.
Ready?
Great job, Adam.
Okay, so what do you think is gonna happen?
Okay, I'm just gonna stand here with this
You
for...
think it'll fit?
I think it'll
Okay, it's gotta come over and say, excuse me, and put your way in.
Oh, fun. It's blue.
Okay.
Don't get your face to it. Never do that.
Oh, it's getting hard.
See if you can get it close to the fire.
Oh, what's that?
It changed color.
Of copper sulfate. Copper sulfate. How am I supposed to get it in here?
That's interesting.
How on earth are you supposed to write that down?
Which 2 milliliters? Blue until shaken, then you dark blue.
Interesting stuff.
Are you about this nigga?
Yeah.
You can do it, Ella. It's not gonna explode or anything.
It's solidified as soon as it hit the bottom.
Yeah, we can't bother.
Are you supposed to stir it?
Pick it up so you can see it better off that blue surface. There you go. There you go.
I do not appreciate that.
You have precipitate.
Yeah.
Cool.
Yeah, but it's...
Whoa!
Did it turn this into a solid?
Look at that. You do. You have a precipitate, don't you? Check that out. Don't put that on your face.
Solid now?
yeah.
That's pretty daggone cool, huh?
During reaction,